Okay, so we've been talking about accretion disks. So here's a black hole, and here's an accretion disk. Let's say it has the inner edge right there. Material is rotating around, so it's going pretty fast at the inner edge. It's going a little slower. Let's say the material is rotating that way. I don't know, let's make an arrow representing the speed of the material, and it's rotating in that direction. So we have an accretion disk out there. There's some outer edge where it kind of gets messy out there. Material is funneled in, it starts to flatten out, and the inner regions is sort of flat, and it's radiating its energy as it falls in, and we've developed an angular momentum profile as a function of this radial distance. And we saw its values. We saw plus values and minus values. So the plus values indicate the angular momentum as a function of r if the black hole is rotating in the same direction as the material. Right, so it's co-rotating. And the L minus represents a situation when the material rotates this way, and the black hole rotates in the opposite direction. That's a counter-rotating accretion disk. And the inner edge of the disk depends on whether you're rotating and counter-rotating and the value of the spin. So sort of in a dimensionless way, usually use the symbol A for spin. And that spin value can go from, so it can be not spinning from 0 all the way to, well, from 0, so it's greater than or equal to 0 and less than about 1. It's really, there's a limit that brings it close to 1, very close to 1, but not actually 1. And so we can work out, the material comes to the inner edge, and that inner edge is further away, the greater the spin and the greater the spin and for counter rotation, and it's closer in for co-rotation. We can sort of motivate this. But here are the values of the inner edge. So I've evaluated the angular momentum at the inner edge for co-rotating and counter-rotating disks. Actually, this comes from a color plot. So this is counter-rotating here. So we have a high-spinning black hole. It's really close to the limit here. It's really 0.998 for the value of the spin. A dimensionless way of describing the angular momentum of the black hole. And so the inner edge of the disk is further out, and so there's a lot of angular momentum. And as the black hole absorbs that angular momentum, the inner edge moves further in, and there's less angular momentum at the inner edge, continuously spinning the black hole down. Eventually we get to 0 spin, and there's angular momentum at the inner edge. The inner edge is the closest to the black hole at this point compared to all these other values of angular momentum. And the inner edge continues to move towards the black hole as the black hole accretes. Now we're in co-rotation, right? There's less angular momentum compared to the value at high spin in counter-rotation. We continue to spin the black hole up now. And we can also get a sense of why it takes less time to spin a black hole down to 0 spin than it does to spin it up to high spin, given the values of angular momentum.